and let's see if this works.
Got it.
It didn't last time, but I guess
I clicked got it. It gave me a prompt.
Great.
Oh, it's a live stream. That's fancy.
Yes, yes.
Okay, let's see what we have here in terms of screen sharing.
Last time, but I guess
I clicked got it. It gave me a prompt. Okay, there's about a 15-second latency right now. Let's see if this works. I have two screens, so there's a fairly decent chance it won't work. How's it look right now?
Okay, it looks good. It looks like the screen that you wanted to share, and I managed to mute the YouTube live stream. So
I see. So that's just the sound of it.
yes. And I'm going to put up a poll. It's kind of a meaningless poll that we use just to take attendance. Nice.
Yeah, just lost my mouse there. And see if I can't see the cursor anymore. Okay, no cursor.
Terrific. So
we're still early.
Yes. Okay, let's go.
Don't mind, I'm going to mute.
Sure, that's fine.
Get a minute or two from the. There they are. And I've unmuted.
Great. Okay, still got a couple minutes.
Yeah.
So Kubra is going to introduce you.
Okay.
Yeah, see, it was interesting. Is just a cultural differences at MIT. People would show up around the right time, maybe a couple minutes late, and it was just understood that everything would start 5 after. And WPI, they come in 5 to 10 minutes beforehand, and you start right on time. So the small talk happens before the appointed hour.
As long as everyone knows what to expect.
Right, right.
I mean, so I've been or was, a manager for a long period of time. And someone pointed out, you shouldn't punish the people who are on time.
Right, right. Exactly.
So starting on time, there's a lot to be said for it. So that's a mixed bag. See, there's always the issue about where to put the faces of the people.
Oh, yes, yes.
All right. So I moved you guys down to the lower screen. But I don't seem to be able to escape from the presentation mode. So hopefully everything will work, because I don't know how to get out.
All right.
Try to work it out later.
Looks like it's working.
Yeah, no, I was hoping to move it again, but I can't move it. So now it's too, no, I'm doomed.
Okay. Great. See, Aaron Deskins, it's good to see you, Aaron.
Howdy.
Well, this might be interesting to some chemical engineers as well as materials people.
Good. They might disagree and say that they're materials people too.
Could be.
You know, I've had that conversation today already.
Oh dear.
Oh, in the most friendly and constructive way.
Well, of course, I have to be a closeted chemical engineer because technically in the mechanical department. But
I won't tell.
thank you. I hope nobody overheard.
Yeah, exactly. Except for the fact that it's the YouTube live stream. Can't change it.
Okay, well, why don't we go ahead? So welcome everyone again to the Materials and Manufacturing and partly Chemical Engineering seminar today. We have an outside speaker today whom Kubra Karaikis will introduce in just a moment. Next week we have Xu Mao, who's the WPI in our materials program. And then after that, a couple of additional outside speakers. I think 2 weeks is, if I'm correct, it's Teresa Pollock, followed by Teresa Pollock at UC Santa Barbara, who also does some multi-scale modeling similar to Jim, and followed by at Boston Metal, Rich Bradshaw, Boston Metal, on zero emissions iron making. So Kubra, you can go ahead and introduce Jim.
I have one single slide. Shall I share it?
If you can.
Okay, so Jim, if you could take down your sharing.
Yeah, that's what I'm having trouble doing.
Oh dear.
Yeah, I outsmarted myself here. So, I mean, I could try some more elaborate things. I'm a little bit afraid of, well, let's just do it, okay? I may have to, if I see you all in a little while, let's see what happens here. I'm forcing something to quit. All right, so it worked. Now my presentation is gone. That's the downside.
Go ahead, Kubra.
So go ahead and put up your slide while you're, if you can.
Okay, thank you. Can you see it now?
I can see me.
Okay, this is the slide. Okay, so today we have, as Professor Powell already introduced, today we have Dr. James Warren as our guest speaker. It's a great pleasure for me to introduce him. Dr. Warren is currently director of the Materials Genome Program in the Material Measurement Laboratory of the National Institute of Standards and Technology, also known as NIST. He received his PhD in theoretical physics at the University of California, Santa Barbara in 1992, and followed his research as a National Research Council postdoc in the Metallurgy Division at NIST. In 2001, he co-founded and directed the NIST Center for the Theoretical and Computational Materials Science. From 2010 to 11, he crafted the founding white paper on the administration's Materials Genome Initiative, known as MGI. Since 2012, he has been serving as the executive secretary of the NSTC MGI subcommittee. His research interests lie in the developing models of materials phenomena and the tools to enable the solution of these models. His specific foci over the years has included solidification, pattern formation, grain structures, creep, diffusion, wetting, and spreading in metals. So today he will give us a talk on the Materials Genome Initiative, artificial intelligence, and the MGS plan for the next 10 years. We are excited to have him here, and we look forward to learn more from him. With that, let's welcome Professor Warren, and I can stop sharing my screen now. You are welcome to your screen.
All right, let's see if we can get it back.
Okay, hopefully.
There it is again. All right. All right, so we see?
Yes.
Excellent. All right, so I know I saw one of these presentations once where the speaker did not realize that he had been disconnected and gave his entire presentation not knowing. So this is the nightmare, right? So at the beginning, everyone was like, you're on mute, we can't hear you, right? That was the thing we probably heard the most was you're muted or didn't hear it. Now people are paranoid, and so they're always going, can you hear me? So it's just a moving set of protocols. All right, so thank you very much for the kind introduction. And this is not a technical talk in any particular sense. So I would hope that it reaches all of you at some level, although that tends to spur a lot of conversation around a bunch of sort of more policy related issues that I've been involved in now for more than 10 years. But really, you know, my passion for this stuff started fairly early in my career when we were trying to figure out better ways to do science that move us beyond the sort of standard publish and then hope some other people read your paper model that most of science is driven around. So this is a fairly sophisticated audience of materials people, so I'm not going to spend a lot of time explaining what the main issues are in materials, because I'm sure you're familiar with those, but it will hopefully give you some perspective on sort of how we're trying to deal with this, where the infrastructure questions are, and things like that. I'll talk a little bit about AI, and of course, this is a forward look at the next decade of this initiative, which has now been in place since June of 2011. All right, so I always have to start. This has been the joke slide that I've had, but I can't tell from the audience, you know, if you're laughing or not. So we'll just have to leave it at that. So it's sort of a units joke. So here's an outline. So I'm going to give you a little bit of a look back at the MGI, how NIST is supporting the Materials Genome Initiative, how this is all sort of connected to AI, and it's at a fairly profound level. And then I'll talk a lot about the data challenges that sort of keep me awake and how we've been trying to attack the problem. Right? And my goal here is to end, I think target is 1:15. I believe, Adam, that's right. Please stop me if there's a problem or give me a warning if we're running into time issues, but people hate it when you run over. So I'm going to do my darndest to keep it on time so everyone will have some expectation that I'll be done jabbering at a certain point, and hopefully we'll have some questions at that point. All right, so M obviously is the Materials Genome Initiative, so I don't really need to explain material science to this crowd. As we all know, modeling material systems is hard. Here's just an example of two different annealing curves for the identical composition alloy, and you wouldn't be surprised to know that these two pieces of metal have very different mechanical properties, for example, even though they're exactly the same composition. So we all know that both the ingredients in the recipe matter for making materials. But what's changed in the last 10 years and what's changed in the last, say, 20 to 25 years is that our ability to model such systems is actually quite good. And so we can now attack from a sort of more first principles perspective a lot of these problems. And this is really what has given rise to the MGI in some sense. What was once intractable is now tractable. So if you sort of think about the natural evolution of modeling, right on the left, you see CAD and things like that. And then you see more into the finite element picture. And then down below, you'll see something where you're seeing more of a crystal growth simulation in the lower right corner. And as we sort of have evolved our ability to model systems, we start to see how we can sort of attack with generic tools some of the sort of profound questions and how we can engineer and co-design materials along with manufactured products. And so it's all one and the same. So what is the G, right? Of course, this Materials Genome Initiative, and there are two groups of people that don't like the name Materials Genome Initiative, and those are material scientists and biologists, because it's a metaphor. And scientists don't particularly like metaphors, they like precision. And here you're looking at something which is just an attempt to suggest the idea and build off ideas around the Human Genome Initiative, that basic knowledge can be used to sort of allow you to make predictions and understand property. So it's an initiative, the MGI. So what does it mean to be an initiative? All an initiative is something where the president says, here is a problem that is bigger than the mission of any single agency. And it would be good if the agencies work together to attack this problem. So in this particular case, the Department of Energy, National Science Foundation, NIST, Department of Defense, and NASA in particular, all sort of stood up and said, yeah, we want to work on this. This is important. And this is coordinated through this National Science and Technology Council. And we all sort of meet on a pretty regular basis to talk about our programs, develop strategies, and sort of leverage off each other. And that's really all an initiative is. It's now spanned 3 administrations and is going strong. So the original white paper that came out in 2011 and basically said that we wanted to decrease the time to market by half while keeping costs down for the insertion of new materials into manufactured products, right? So that was the goal. And of course, the method really matters. So here's this Venn diagram that we put together that basically says there's experimental tools, computational tools, and digital data are the heart of the so-called materials innovation infrastructure. And these ideas aren't terribly profound or new. Those ideas are really the heart of all science and engineering. The basic and important idea that's somewhat different is the tightness of the integration of these. So instead of just doing an experiment, measuring some stuff, publishing that, throwing it over the wall, here you want to try to do things in as close to a closed loop as possible, where you're moving the information around and trying to accelerate the materials design problem to the maximum level that you can. And if you could do this and could design new materials more quickly, you could then, of course, achieve good things. And that's what the ring around the outside is, around health, human welfare, national security, energy production. And there's this extra core element here, which is this next gen workforce, which is sort of an outlier in that it doesn't really fit in with the rest of the picture, but is actually fundamentally essential. And it's particularly when I talk to universities, want to emphasize this. A lot of the tools here that are being developed are open access, open source by necessity, because you're working in a pre-intellectual property environment. And so you could sort of ask the question, as a nation, here we are making these investments supposed to help our economy, help us. How can we make that happen in this open environment where anybody in the world could use these tools? And of course, the answer is we need to have the talent to use these tools. So without the educated, sophisticated workforce, we can't do any of this. So it's literally the heart of how this gets done. And of course, it also has to span the full discovery to deployment continuum. And so we're really looking at a heavy lift here, right? We're looking at all the way out to manufacturing. And so the MGI has a lot of work to do. And while we've made a huge amount of progress in the last decade, there's still a lot more to do. And there's a lot of energy that's now going into looking at how to make contacts with manufacturing, something that I know WPI has a lot of success in. All right, so here is the sort of one slide vision of what the MGI is sort of trying to do. And this is an old slide of mine. And you see down at the bottom a loop that describes a sort of multi-scale modeling process from quantum scale all the way to macro scale. And it's this fantasy, particularly among modelers, that you could somehow model all the way up the late scales and just solve the problem, right? But of course, it's in some sense a lie. It's really hard to do this. And if you look, you'll see I've got information flows going all the way here. To do these modeling things, you need to pick what data you're going to use as inputs. You need to choose which models you're actually going to use. You need to move the information around. You need to know whether that information is any good. You need to make a lot of approximations along the way, which is another whole set of choices. And so there's a huge information management and knowledge management problem that lies at the heart of the MGI to make these predictions. And so you can sort of view the infrastructure for the MGI as a way of how do you create and capture knowledge about materials and use it in a maximally efficient way. And I'll be trying to frame the discussion around that. Now, I just mentioned multi-scale modeling. I think that was a cool thing that I used to talk about back in the 90s. It's certainly not something you hear a lot of anymore, at least with this name. These ideas just aren't new. There are companies that have been doing these things for a long time. And so the MGI in some sense really isn't about how do you do this, although there are some interesting questions there about how to do it best or better. The real question is how do we make it easier for more people, right? So how do we lower the barriers so that it's possible, instead of it just being, say, Apple, who, when they released these watches, very excited because they did the alloy design. They co-designed the alloys with the watch, right? So this was one of the first public examples that we had seen where it was about a 2-year development time for the alloy for a consumer electronics product, but it was still really cool, right? And they talked about how hard the metal was in various cases. And then if you take a look at, say, Tesla SpaceX, it's absolutely mind-boggling the kind of co-design they're now doing of alloys. In the case of SpaceX, saw a presentation there where they're now down to 18 months from design of the alloy to insertion in a rocket, which is it used to be 18 years. I mean, that's mind-boggling. Okay, so there are often examples in the case of materials of insertion where it's 30 years. So to get it to 18 months is almost instantaneous. So, as I said, these ideas aren't new. Here's another nice example. This came from Kevin Anderson at Mercury Marine, right? So here you're designing, outboard motors for boats, right? Something that you wouldn't necessarily think of as a technologically terribly sophisticated product, but here you are with it fully integrated in their sort of corporate culture. Again, so the idea is not new, but you need a lot of good things to happen, both at a sort of human level. You need advocates to make this happen, and then they can really see the benefits to the corporate bottom line. So there are monetary reasons to do this, but there are real barriers. And in fact, NIST commissioned what's called a prospective economic study, where they said, well, what if everybody in manufacturing were able to do this kind of MGI style approach in their own product development? And the answer is it would be worth about $100 to $200 billion a year. Now, I looked at the models that they used for the economic projections. To say that they're not very sophisticated would be fair, but we're professional modelers, so that's why there are the error bars that you see there. But it's still a big number, even if it's off by 50% too high. So here's a summary of the MGI. Right, the MGI is really about our ability to design and deploy new materials faster. But to do that, we really need better, or just any data and models. We need to make decisions there. If you sort of think about it, take a step back, it's really a direct consequence of our improvements in computational power that allowed us to make these models or solve these models. But it's also coupled to this disruptive consequence of the internet. And I'm going to talk a lot about data management and data sharing in a minute. And before the internet, a lot of the issues around knowledge sharing and data sharing were, well, okay, that's great, but how? After the internet becomes pervasive, the question isn't how, it's how, like, how come not? This should be easier than it is. It's obvious in some sense that we should be able to share this stuff better, move it around better. Right. Okay, so then you could say, well, how do I get this information? You know, what's the fuel, right? And so some of the early successes were in high throughput computation, where the computations got cheap enough that you could generate large amounts of data that would then feed this knowledge monster. Or you could try to figure out ways to do a lot of high throughput experiments. You want to ensure quality there at the same time, ideally. Or, and here's the sort of big fantasy, right? We want to try to get the information somehow from everywhere, which would mean you would have to mine the literature, mine published data if the data is published. And that means we really need to change the publication models. And so a lot of our intellectual energy has gone into how do you publish data? How do you do that better? And I'm going to talk a fair bit about that. Okay. So in 2013, when NIST decided to get involved with the MGI, we developed our own plan, and you'll see the document looks familiar for our own role. I really hope this, I just did the advance and nothing happened. Uh-oh. I'm experiencing technical difficulties. So I am tempted to kill the presentation and restart it. And hope that works. Okay, I got my cursor back. That's good. Let's try this again first, though. Look at that. Okay. I just scared it and it got better. Okay. So here again is this picture that I showed you at the beginning, the sort of vision of the whole data infrastructure, modeling infrastructure. How can this support this? And so we decided to approach this with three main foci, right? So on the left top, you'll see, well, let's talk about the right first. So assess and improve the quality of data and models. And everywhere, this is always data and models. Well, that's a classic NIST thing to do. You know, we're always about delivering that extra decimal point of accuracy. We're really good at understanding the models. We should be able to help other people to assess the quality of the information that they're getting. And we thought we would spend a lot of our energy on that, and we continue to do so. We also knew that we had to think about this data exchange problem, right? There could be some standards. How do you move the data around? How do you move it in this modeling pipeline? And put some repositories in place to store the data. What we didn't really appreciate was that while you can say, that's not that interesting, it's a technical set of details, turns out it's hard. It's actually technically really interesting and non-trivial. And we spent a huge amount of our time now thinking about that part of the problem. In principle, though, once you solve it, or at least solve it in part, you can then focus on the third area down in orange below, which is new methods and metrologies like data-driven analysis and models. Now, when we wrote that in 2013, we knew that there would be some data-driven science that could happen, but we didn't fully appreciate just how quickly AI was going to sort of come up as a real powerful technique to accelerate materials design. But I'll give us some credit for recognizing that this was instrumental, this infrastructure, in making that happen. So as AI has become more and more relevant, we're ready. And in fact, I'm going to talk a lot about how it inserts directly. Okay. So I think I have figured out now that there's one button I should not hit. Okay. All right. So I have this little thing I want to talk about data quality. I've been showing this part of the presentation for more than 10 years now. And I think it's very sort of important. It lies at the heart of stuff that I've been doing at NIST since at least like 1997. So, right. We're going to talk about this in the context of AI as well. Okay, so here's an instrument, right? So hopefully some of you have seen one of these before, but basically someone will say, let's do an experiment. Let's measure the modulus of some steel, right? And so you put this thing in here and you pull on it, and maybe you like the answer, so you record it in an Excel spreadsheet. And if it's interesting enough, maybe you'll publish it. And the publication is essentially a lot of metadata around the modulus that you're measuring. Okay. but of course, you're not measuring modulus, right? Modulus is that, well, fourth rank tensor technically that I've written there in the first line. It's a model, it's an equation, it's not true, right? It's an approximation of some kind. And what you're measuring at best is some length change and assuming that the model is true. And so if you only publish the modulus and not all of the experimental data, you have done the community a huge disservice because it's wrong, right? And so there's this really, really profound disconnect in a lot of particularly experimental minds about the truth of models that gets in the way of the proper publication of data. But it's even more profound than that. So I love this example, right? So this is a picture of LIGO, right? So the gravity interferometer that won the Nobel Prize, I think in 2017 or something like that, for just detecting gravity waves, right? And it's an interferometer, it's two arms, right, like this, right? And they're shooting lasers down these beams, and the gravity wave moves through the detectors, and by detecting the distortion in the interference pattern between those two lasers, they can measure strain, essentially, of space-time. Okay, and I don't know, does anybody out there know how much strain it is? It's like 10 to the minus 22. Okay, it's insane. All right, and so, but with this, they measure what they said they measured were two black holes spiraling to collide 1.3 billion light years from Earth. Now, is that what they measured? No. Of course, they didn't measure that. What they did was they took the Einstein equations that model general relativity, right? Solved it for two black holes spiraling and colliding to each other, figured out what that signal would look like, and then compared that signal with what they measured in the detector. Okay, so again, without the model, you can't make the measurement. And this is in general true. Okay, you need some kind of fundamental understanding of what's going on in reality to make a measurement. Steve. Hit the wrong button. Oh, oops, that's the wrong way. Oh, God. I don't know what's going on. Click there. Okay, just the space bar. Only hitting the space bar from now on. Okay, here's another example. This is more physics. I guess my training in physics is coming out here. Large Hadron Collider. You're measuring, you're getting about a petabyte a second of data off the collider. When you save the data, you save about a gigabyte a second. So that's a 6 order of magnitude data reduction. How can you do that? Well, the answer is, of course, you've got the standard model. The standard model is really, really good. It's really, really accurate. So if you have super good model, you're in good shape. At the other end, maybe bio, right? There maybe you don't have a whole lot of quantitative models. So there you're going to be saving a lot more data. And if you go and look at where there's been a lot of informatics work in the last 30 years, it's in bio, right? That's where we can learn a lot from them. Materials sort of sits in this nice middle ground. I've spent most of my career trying to turn materials more into a physics problem, but you can make a pretty good argument that we got a lot to learn from the data people. And, you know, I was giving this talk again before AI became a thing. And now I'm like, well, duh. Okay. So this is sort of where we're coming with this, and we're sort of full circle on this. Right. And if you think about it even harder, all that a physics model is just a really, really compact way of writing a lot of knowledge. Right. But it all came from the same idea as data driven. It just happens to be that we can encapsulate it in a small equation. Sometimes it gets encapsulated in the database because we don't have a clever way yet of describing it. Okay. Right. So AI and ML, machine learning, is really a true enabler and driver for MGI. And because it's really just another system for generating a model. Right. So that's sort of where I wanted to get to. Right. Was this sort of notion that all that AI is handing you is, instead of saying, okay, here's Newton's equations, here's a relationship between stress and strain, or whatever it is that we think is true or more true, Instead, we're going to use this AI system, which will also give us predictive power, given some inputs to predict something about some outputs. And that's all we can hope to do. So here's a lovely example. It's now, I guess, 5 years old. It was the first time I'd ever seen AI techniques applied to a material system. And the first time I saw it, I thought that the guy who was telling me was frankly full of it. And because it was impossible what he was describing. He was showing, and by the time he was done, I was amazed. So here they were taking a ternary alloy system and essentially depositing it onto a silicon plate. And so you have all the compositional variations from like a Gibbs triangle, like is shown in the lower right corner. And then rastering an X-ray, in this case in a synchrotron, across the sample over and over again. And all you're looking for here is you get the X-ray spectrum off, or the diffraction pattern off the rastering beam. And at some point it changes. And so it doesn't matter what the crystal structure was that it was measuring from the diffraction pattern. All that matters is that at some point it jumps. And so if you're able to detect pattern changes, right, you can detect these boundaries between crystal structures. And that's, of course, the phase diagram. So this thing was able to compute the phase diagram really fast, or measure the phase diagram very quickly for these thin film systems, just by using these sort of pattern detection systems from AI. And so when I saw that, I was like, wow, this is incredible. But it's even better than that, right? So then they started saying, well, instead of rastering like this, what if I just say, do a very coarse grain, high level look at 5 points and then say, okay, where should I measure next to give me the most information, i.e. where do I know the least maximum uncertainty? And so you see this red dot that's hopping around on the left, that's the algorithm now picking the new spot based on maximum uncertainty. And this thing now starts to converge to the correct phase diagram way more quickly than it would otherwise. And actually the guys who did this work hated that I still show this movie, because they've of course gotten it so it goes way much faster than it does in this simulation already. But it's even cooler than this, because the second that you start to think about this and you say, well, where should I measure next to get the most information? You start to realize that you should instead say, what experiment should I do next? Okay, and so you don't even need to make the whole sample, right? You just make it where you want to measure next. And so this is where you get into this notion of autonomous science, right? So if you get an AI and put it into the loop, it can then decide what system to synthesize next. And then you do the characterization test, and then you do the analytics, and you go back and you do it again. So you're starting to see how you could put robots into the lab, put AIs in charge of them in some sense, and get the postdocs and graduate students to do much more interesting problems than some of the things that we're currently asking them to do, because this part, at least, we can automate more. So it's a very exciting time, I think, to be a scientist, because I think that the exploration of compositional and processing space is about to be blown kind of wide open. And if you look in the chemistry side of things, it's already happening broadly. I think in materials, we still got a lot of interesting things to do. And I think it's going to be dominating our discussions for the next number of years. So I'm excited. So I like this example here. And this was taken from some work by colleagues at NIST a few years ago, where they actually did a sort of traditional integrated computational materials engineering modeling problem to design a new alloy for the nickel. And so this is something, I didn't know much about in terms of, how one would do this particular set of alloy design problem. And one of the things that I thought was particularly cool, right? You walk down the property side of the list, which is where most people are comfortable, right? So you've got the color, the density. You don't want yellow nickels, right? He's got to be the right color. Although probably most people haven't touched any money since the pandemic started. It's kind of weird, actually. But, it can't be too expensive. Obviously, big issue here was cost. The nickel was costing more than a nickel. And so you got an issue there. one of the properties that matters the most, it turns out, is electrical conductivity, because otherwise it won't work in the vending machine. And so the basic point on this diagram here, though, right, is that each one of these arrows is in fact a model, right? That's how you link a property to the local microstructure, how you link the processing additions to the microstructure, etc. And so everywhere you see a line here, it could be replaced by an AI. You know, whether or not you want to do that is a separate question. And usually when you want to do it is one of two reasons. One is you don't have a model. And so you're just going to do something completely data-driven, which effectively gives you a model. Or often it's the case that an AI will be many orders of magnitude faster than a traditional modeling approach. And so you can imagine replacing it there. And in fact, you can use AIs to obliterate large parts of this diagram and just sort of connect processing, say, to properties. You know, that can be risky. Okay, right? The model can fall apart on you in ways that you may not understand. But nonetheless, a lot of opportunity. Okay. So now I'm going to talk about policy and the strategy of the MGI. I'm keeping it on time here. So here is the 2014 strategic plan. It came out in December of 2014, so we just got under the wire. So beginning of 2015, it's rolled out to most people. And we really had four main goals. We wanted to lead this culture shift in how material science is done, to try to get more of an integrated team approach, because you really need to do the modeling and the computation and the experiment and the data management all really at the same time. And as you'll see, we basically declared victory on that one. I think that there's broad understanding that that's really the way things need to do. And then we really need to achieve this integration. That's the second goal. We really had a lot of focus on digital data at the time, and we still do. That's because, of course, the data part of this problem is the new and interesting part in some sense. Everything else we thought about at some level before, but the data piece, nobody had really thought about. And then, of course, the workforce issues that I think will remain paramount. So here is what is likely to be the strategic plan. So you're getting a preview of the goals and objectives.
你做的吗？
Somebody is not muted.
哦，
之前讲手机面你感受一下，
哪里搞的？
就那个 V
One Chin Lu, please
哦，
mute.
你买的。
招把可以。
Thank you. All right, back to work. So three main goals. So now we're talking about unifying this infrastructure that we talked about before. And then we have these objectives underneath that goal. And I'm going to spend a fair bit of time talking about the so-called National Materials Data Network that we need to establish. And then, of course, there's also all of these issues, again, around how do we harness this data and get it into the hands of people who want to do AI, particularly in industry. Okay, and a lot of other elements here. So, okay, so data infrastructure. How do we get more data? So in 2017, TMS put out this publication. Chuck Ward was the lead on the study on the status of the so-called materials data infrastructure. How do we construct it? And they came up with a bunch of recommendations. And I found it fascinating to go back and look at them now a few years after the fact. And so the first one was strengthen the materials data infrastructure core and repositories, registries, tool development. I think we've been doing a good job there. Recommendation 2, sustain and grow the infrastructure, dedicated funding programs. Well, I don't know how much we've grown them, maybe a bit, not a lot. We could definitely grow them by several orders of magnitude more, and we haven't done that. Recommendation 3, create, execute, and monitor incentive mechanisms. Nope, I don't think we've done almost anything on that front. And I'm going to spend almost all of the rest of the talk, the next 5 or so minutes, talking about our failure there and how to address it. So what's stopping us from living the dream? How do we get to MGI 10 or X? It's all incentive failures, okay? And the incentive failures come down to, I think, 3 levels. There's this sort of generic lack of information 50% of failure. This is easy to fix, right? Which is you can't act on a better practice, a new way of managing data if you don't know anything about it, right? So the way we do that is we teach, we give talks, we go out there, we tell people, and if it looks awesome, they'll do it. So it's not much of a problem. Now, then there are the technical problems, right? So these are the ones that a lot of us like to think about. You know, what kind of tools do we need? How do we manage here? How do we add more metadata to this problem? You know, what kind of capacities are actually needed? We can try to anticipate it. We can look at other communities and try to solve it. We may be right, we may not be. And so, you know, the example we've been working from is the astronomy community, where they've had enormous success in sharing all their data. They like to joke because they had astronomers, so they're allowed to make fun of themselves, that the reason it's so easy to share astronomy data is because the data is worthless. And, you know, I know what they meant by that. If you compare it with a materials thing, you're not going to make a lot of money off astronomy data, right? But, you know, if you take a look at the data from the Hubble, for every paper that's written about data that's gathered from the Hubble, 2 out of 3 papers were not written by the PIs that took the data, right? So you're getting about a factor of 3 in terms of the number of papers, if you think that's an interesting metric, over what you would have gotten if you had just had the PIs have the data. So you're doing way better. And so you can imagine for materials, we can sort of try to develop similar infrastructures. And so if you think about what the astronomers are doing with the virtual observatory, they get a position in the sky, and they basically get a measurement type, which is just a frequency of light, and they can get all the data about that point in the sky in a solid angle around it from all the world's telescopes. It's absolutely amazing, right? Now, how would we have the same kind of thing in materials? And this is a slide stolen from Zach Trott. Right here, materials is significantly more complicated because we have the processing history and the synthesis history. But even so, it's not impossible, it's just big. Right. So as I like to say, pick a box on the right and get to work. How do we share data in one of those boxes? Right. Can we do it? And I think the answer ultimately is yes. But we probably want to think about which problems to solve first. So as I say, what is our telescope here? And I would claim that we have some pretty good ideas. Probably the single most important set of measurement capacities that we have, and it's sort of ironic because I showed the Large Hadron Collider, which is most of the light sources and beamlines in the country now aren't there to do high energy nuclear physics. They're there to do material science, right? That's what we do now, mostly with beamlines. And the amount of data that's coming off these beamlines is growing essentially the Moore's law. These are expensive data, right? They, there are a lot of arguments to be made that we need to do a better job managing it. And all of the facilities that have detectors now understand this and are trying to solve this problem. And so if you talk to people who normally go to beamlines to do their research, they used to come home, you know, they have a bookshelf full of hard drives. So that's, you know, sort of where things are. So that's the technical. Now let's talk about the professional. This is really where all the bodies are buried and the problem we need to address. And people will talk about this all the time. And what they'll say is, I really have no reason to share my data. In fact, it'd be nice if other people shared their data, but I don't have time to share mine, or I don't want to share mine, right? And incentives are influenced by behavior. I love this meme, right? Describing how we respond to different people. So this example of Galileo is useful. So about, I don't know, was it 500 years ago now? A long time ago, Galileo was a famous guy because he pointed his telescope at Jupiter and found the moons of Jupiter obeying the same laws, essentially, in a heavenly body that we knew were behaved on Earth. And so this is a profound discovery. He then eventually pointed his telescope at Saturn and thought he had found the moons. It turns out he'd actually found the rings, but his telescope wasn't good enough. But to sort of cement his priority in the discovery of the moons of Saturn, he wrote an anagram, 37 letters long, that he could decode and prove that he had made this discovery, but he didn't have to tell anybody what he had found. And so he could keep it secret and not give his competitors any technical edge. And I still believe to this day that all scientists would behave this way if they were allowed to. But the reality is we don't let them do this anymore. If you take funding from government or from most other funding sources, you have to publish. And that's sort of a rule that evolved. You know, and partly it was the funders. Oopsie, that's interesting. Let's see if we can bring that back. Okay, that's better. And so, you know, what I like to say is we need to, there we go, right? We need to both change the rules and give people the tools to make it easier to publish data. And so we've been focusing a lot on not so much the rules, but the tools. And this gets into this whole notion of fair data, which hopefully some of you are familiar with: findable, accessible, interoperable, and reusable data. Okay, so in addressing this real issue around priority and fame, right, what I would claim is that until people can do science and engineering on various platforms associated with the materials data infrastructure, the data sharing won't happen. So all of the reasons that people do science are the reasons that you would want people to share data, right? You want to be able to combine data sets with other existing data sets. You want to build on prior work. You want to be able to visualize your results. You want to find interrelationships between data. You want to use AI and machine learning on this information. The sharing of data is a side effect. It has to be a side effect. If the primary goal of a platform is just data sharing, it's nothing. It's not going to be very useful to almost anybody. And this is because, of course, scientists have a very specific set of incentives, basically around fame. I mean, it's famous among 100 people, but that's what it is. And if you're in a business, then your answer is money. But it's the same thing. You want tools to allow you to make money or to become a better scientist or to do better science. And so until you can get this incentive problem sorted, you're not going to solve the problem. So how do we go about as a community getting the infrastructure to the place where it actually allows us to do better science and engineering, right? And so I would claim what we actually need is social, right? We need a network of people that can collaborate to have an ongoing conversation, right, about what is needed to get the infrastructure to the place where it delivers on the platform descriptions that I just gave. And this has to span academia, government, and industry. And we need to have, road mapping discussions and technical discussions about how to do it. And then we can turn around once we have those roadmaps and say to the funding agencies who do not like to get out in front of the community, hey, these are priorities for our community and we want these things. And the more that we can do that, the more they will get funded and the more the infrastructure will be constructed. All right. So there have been some efforts towards this in the last year or so. There's something called the Materials Research Data Alliance, which could be an instantiation of the National Materials Data Network. I'm optimistic. Trying to find ways to support that right now. So I'd be happy to try to help people if they're interested. That's the URL below, which reminds me, anybody that wants a copy of this talk is welcome to it. Just let me know. And with that, I will take questions. So thanks for your attention.
Thank you, Dr. Warren. It was very nice talk.
So would you say it's a good time to go into material science, like to enter into the field or the workforce?
Wow, jump right to a tough question there. Yeah, of course. I mean, it's funny. I was talking with some of the other faculty before, and I know that you guys are also involved with the, your mechanical engineering. I mean, what fraction of the mechanical engineering department is getting its money to do materials research? There's a lot of money still coming from the government materials research. Obviously, everything's made out of materials. And frankly, hopefully you'll see this in our strategic plan when it comes out, there are a lot of really big problems in the world, right? Materials are going to play important roles in addressing some of those problems. It's essential. right? Whether it's mitigating some of the problems that we've had with the use of materials in prior years, or it's associated with finding better ways to do it, or how do we do direct carbon capture, or how do we make better solar cells or wind turbines, or, you know, filters for water, or, I mean, you could just go on and on and on with all of the issues that the world is facing in terms of making this place a better place to live, and the critical role that materials is going to play at every step of the way in that problem. So it's as a driving force, I think it's huge, right? The only probably better sales job you'll get is from biology, because everyone wants to live forever. But beyond that, quality of life issues, I think materials is no slouch. Anyone else? I see hands up. Should I be running the show on this?
Well, I'll jump in.
Okay. Go for it.
Thanks for a very interesting and thought-provoking talk.
Mhm.
I work in surface metrology,
Okay,
and while everything's made of materials, surfaces cover everything.
sure.
And I liked in particular your discussion of the measurement issues and how many times we have to measure to figure out what's going on, and that works nicely with some of the stuff I'm doing. Surface metrology is terribly underfunded, especially in the United States compared to Europe. And the only thing we can touch is surfaces. The only thing that interacts with things is surfaces. The surfaces are the way into materials. And it's interesting, the misconceptions that people have that are based around measurements. And I liked your emphasis on when we're pulling this. Are we measuring the elastic modulus? No. Actually, we're measuring resistance probably in a Wheatstone bridge or something.
Right. Yeah.
And then we're interpreting that as strain, and then all right. So
Right. I didn't even talk about the fact that there's probably is a resistor in most of those systems, and there's some correlate in another layer of modeling. That's right.
Yeah. And the gravity wave stuff's really cool.
Yeah.
We're measuring length.
Right. That's right. That's it.
We're not measuring gravity. We're measuring length.
Measuring length. That's right.
Measuring the effect of gravity.
Mhm.
And surface metrology as practiced in the United States is terrible.
Mhm.
And we look at what the NSF is funding in surface metrology, and it's 1930s, literally 1930s stuff. And so one of the problems is people say, well, I measured the roughness. Yeah, all right. First of all, you don't even know what roughness means.
You don't know what it is, right?
Secondly, you did not measure the roughness. At best, you can calculate the roughness from a measurement. So I was wondering how much you feel we need to distinguish the actual measurement and then whatever kind of parameter we calculate from that may be associated with the phenomena or fit into the model. In other words, how much do we need to distinguish all those steps we make when we use an interferometer or a confocal microscope?
Right. So, I mean, so there are a lot of ways to go on this. Of course, you know, we all enjoy the polemic, but ultimately, you know, the original reason I put together those slides was to convince people that they needed to publish all of their data. Okay, because you don't know what you're talking about, but at least if you tell me what you actually measured, length or whatever it is, or some scattering spectrum or whatever it is, I can then try other models, right? Or maybe I have a better characterization of roughness, whatever that means, than you do, where I'm using some.
But basic measurement is still length.
Oh, yeah, length is hard to get away from. Right.
And it's in surface metrology, you're actually measuring an interaction with the surface over a finite region. You can't measure the height at a point. You can't know the height of all the points on the surface.
Look, sorry, each technique will bring to bear some level of resolution and some ability to characterize the system, and that's going to be the case no matter what. And certainly, I don't want to get into a long digression, particularly about surface science, except to say, you know, if you broaden that to the word interface, which I think is a reasonable thing to do, then almost all of material science is dominated by concerns around transition between one system. Otherwise, you're just talking about bulk systems. So it's completely germane, and some of this becomes just framing. And so if there is, there is always this issue with funding agencies and with academia, and industry to a certain extent, around fashion.
Yeah.
It's like corrosion used to be super cool and now it's not. And then maybe it becomes cool again. So you're always going to be dealing with that. And NIST has had for a very long time and still has a lot of very good people, of course, in surface science, because the metrology issues, they're still there. get away from them. But I think your statements are fair. But I think from the point of view of the MGI, surface science and all of its other issues are critical.
Yeah. The main point was I like you distinguishing between the actual measurement and then calculations based on that measurement and then how those fit with the model. Thank you very much.
Sure.
Could you please raise hand if you have questions? We still have time.
Oh, I see a chat.
Yes, there are questions in the chat.
Wasn't that nice? Thanks, Matt.
I'll point out that
You did.
70% of the respondents to the poll correctly identified that your specialty is materials modeling,
Yeah.
opposed to applied genomics, and 2 people said starting initiatives.
It's funny. I'll give just a little bit of, I don't want to call it insight. That sounds too profound. So I've talked to a number of people who are like, well, how do I do what you're doing? And I'm like, it's hard, right? It's not hard. It's not because I'm super smart or anything like that. Some of it's luck. A lot of it's luck. So you got to sort of remember, so it's a combination of stuff, right? It was issues I cared about my whole life, had the right training, but I also had to be at the right place at the right time, have managers that supported me. And then when the opportunity came along, they let me tag along as the sort of junior guy back in 2011. And then I just managed to hang in there. So that's sort of how I got to do this particular gig. But it's not particularly replicable. But that doesn't mean it can't be. I mean, I have another colleague who seems to be pulling it off right now with circular economy issues. But it does take this combination of luck plus everything else that we know about. So yeah, starting initiatives. That's me. I'm going to go start 3 more.
I think we can close the official portion now, as people have to head off to class or virtual class, as the case may be. But Jim mentioned he's available for a few more minutes if others have some questions to continue on. I saw 2 hands from Yao Shu and from Chris Brown. So if you're stay on for a little while.
Sure, I'd be happy to talk about that.
Okay. Yao, did you have a question?
Yes. Hi, Doctor. Thank you for the presentation. It's super nice and inspiring. I cannot help to stop thinking if I can connect my research to artificial intelligence, if AI can help my research to move better. But when this idea comes in, it just reminds me there is recently a big success in biology field, which is the AlphaFold, which can successfully do the protein folding questions, which has been a huge problem for the field for many years. I was wondering if you have any hints, can give us any hints on in material science, is there such a question
Wow. Great
protein
question.
folding?
Yeah. So I literally have a slide where I say we need to think about that. Okay.
Yep.
So yeah, correct. We need more problems like that. I mean, so another colleague, he said, the bio people, the protein folding people flipped the table, and I love that. Right? They just basically came in there and said, "Remember all that stuff you're working on here? Yeah, we solved it." And obviously they didn't quite solve it, but nonetheless, they may have mooted much of the value of the protein data bank. We'll see. Okay, if that's the case, that is an extraordinary accomplishment. But my guess is that if you start to think about what it is that we need to do, right? So this is in the strategic plan too. We need human genome project level MGI activities. Okay. And so if you start to say, well, protein folding is like that, right? That you have a huge, highly valuable thing that you can compute.
Yep.
So the question is, can you compute it? Right?
Yep.
Or can you measure it? Because if the answer is I can create a high throughput system and measure it at some sufficient level of resolution, it would create a database effectively of extremely valuable information that could then be used for other things. So, right, the only reason protein folding is interesting is because in principle, it gives you some insight on function, which then hopefully you do drug design or whatever it is that you think you want to do, something associated with human health.
Yeah.
So you can certainly imagine in materials that, for example, if we really had all the ternary phase diagrams, all of them,
Oh, yeah.
okay, that'd be pretty good, right? Right now, it's pretty thin out there. And if you get up to ternary, it turns out you can construct with pretty high fidelity, essentially all multi-component phase diagrams. At least if you talk to the CalFab people, they would largely agree with that. So if you talk, I stole this idea from Greg Olson. So, I mean, but so if you ask what the true human genome sort of analog is in materials, that's one of them. Now, I think there's some other grand challenges out there. I think developing and applying CalFed-like methods to polymer systems, I think is another space that would be of incredible value. And would also unify the materials disciplines in a way that they currently are not, which also means working in more notions around time dependence than we currently are comfortable with in metals, because polymers path dependence is way more complicated.
Yep.
But nonetheless, if those are just two examples that I would say represent sort of grand challenge level stuff that is radiantly clear, is high value.
Okay. Thank you, Professor.
Sure.
Anything else? I guess something I've been thinking about is these incentives. How do you create incentives for whether it's open publication of code or open access publication of articles, et cetera? I don't know if you have any thoughts on that.
Well, sure, I have a million thoughts on that. I mean, so look, here's the example I like to use. If I told you, hey, I want to set up a system where I figure out what you're interested in buying and what products you want, and I'm going to create a direct marketing system to sell you all that stuff, you'd like, nah, it's okay, I don't want that. thanks, but no thanks. But if I told you I was going to give you a system that allow you to like say hi to your friends on their birthdays and and put pictures of cats and stuff like that, you'd be like, oh, that sounds pretty cool. Give me some of that, right? So it's the asymmetry, right, between how, say, a social media platform works and why they want the data that is what matters, okay? So what I need to tell you is, hey, Dr. Powell, right? what I want to do is give you a system that allows you to combine your data sets with the Swiss data set, do AI on that system, and predict the next awesome sauce thing, okay? And you'd be like, yeah, give me some of that. Oh, by the way, you have to curate in the following way to get the information out of the system, and then everyone will be allowed to see it. And you'd be like, okay, that's fine, right? That's the incentive problem solved, okay? And we know how to do this. We just need to do the mapping, okay? Because the problem we've been having is mostly I'm just working with true believers, right? If I only work with the people who already appreciate and understand why we need to share data, we're never going to solve the problem. It's not that we can't work on the technical issues around solving it, but we need to convince people that they want that resource. And we need to, and so I like to say it this way. Are you using these data sharing tools? No. Why? Okay, right. I want them to answer the why question and get them say, well, if it did this, okay, then I might do it. Or it doesn't do that, or it's too hard to use. I mean, something. I want a list of things so that we can then turn around and say to the NSF, if we fund this kind of work, it will help, right? It will help science, right? And I think you can get there. So, I mean, they already understand it at some level, but they don't want to get too far in front because they don't want to be the ones that say, because if you fund something, you're not going to fund something else, almost always. But this is important stuff.
Makes sense.
Yeah.
Great, great.
Want to call it?
Any other questions? Sure, glad to call it. Well, thanks very much once again. Thanks, Jim, for a great talk and for some interesting meetings this morning. Thank you, Kubra, for hosting the meeting. Okay, so a note from, actually a question from Montes here. So it doesn't require some sort of initial level of attractiveness before a database becomes large enough to be useful. Well,
sure. I mean, in other words, there's always a sort of bootstrappy problem. And in fact, I've been fighting that bootstrap problem for so long that I'm trying to think about the other way, right? Which is say, why is this not valuable, right? How do we get it to that place? Because a lot of people talk about sustainability, right? The NSF's always asking people about sustainability. And I'm like, that's the wrong question usually.
You mean sustainability of the
effort or the database or whatever.
Okay.
If nobody wants it, forget it. Okay. In other words, sometimes that's a disaster, but it's pretty rare. We decide that something should be paid for by the public sector or by the private sector. That's the system we have. If neither side wants to pay for something, we don't really have a system in place to deal with that.
Yep. So
their existence of NIST is around the idea that the public sector should be doing things that the private sector isn't, right? But at the same time, most of this stuff has got to get solved by an appreciation of incentives, as I said, whether it's fame or fortune, right? So either the private sector is going to see an economic opportunity, right, to generate this kind of platforms, or the public sector will do it because the private sector doesn't see the opportunity yet. But we still decide that it's in the national interest to create this. But that doesn't solve the problem that I was talking about with incentives. Whereas you can create all the infrastructure you want people to use it. Okay, and if you want them to use it, it's got to do something that they want, right?
Well, in this area, we have some examples, right? Like thermo databases, for example. We have Thermocalc and Pandat and FactSage that accumulate and sell these things. So there's a private sector incentive, and there are journals that require you to publish your data in order to get into the journal. So there's a kind of a credit kind of incentive.
Yes. That's a small number of communities, but they're there, right? Okay. Thermo is a nice example.
Okay, all right.
But I wish there were more. Crystallographic is the sort of is the singular example. So highly formatted, very well structured data, really know how to solve the problem there. Thermo data, pretty good. And there are a small number of journals that absolutely require it. The fact that there are 3 or 4 or 5, CalFed companies, basically, it's pretty cool, right? That tells you how valuable it is.
That's true.
It also tells you there's something to think about there, right? Because ultimately, it's not the software that's what's useful, right? It's the data.
Right.
Like the one thing that you pay through the nose for, the databases, quote unquote.
Right.
And so there's some serious disruptive threat with what some of the MGI is doing, because we're trying to figure out ways to generate more data. Okay. So those companies, I have friends that work in them, probably are nervous about some of the stuff that we're talking about, but we need to solve these problems. It's bigger than just Thermocalc's business model. And I don't know what's going to happen. I know that Thermocalc's got a lot of smart people, and if the infrastructure suddenly had more data, if they find a way to solve problems for a lot of engineers that would otherwise be something that they wouldn't want to do, right? So my guess is these companies will benefit, right? They will have to tweak their business model a little bit, but they're going to be able to interoperate with a whole wonderful data resource, and they'll be able to add significant value and be able to make a living doing it. But disruption happens. We're a base, we're in the disruption business. It's really hard to get away from this. We're constantly trying to find new ways to do things, right? Do it better.
Makes sense.
Yep.
Terrific. All right, well, thanks, Montesir, for the question. Thanks very much, Jim.
It was a pleasure.
Terrific.
Hopefully someday, in real life, that'd be great.
Yep. Maybe MS&T. We'll see.
Yeah. All right. Ciao. Thanks, everyone. Thanks for the comments. It was great.
All right. Bye-bye.
Bye.